Welcome, Mrs. Mahoney's podcast. This is our third one in our Unit 7. We are on page 9 in your packet, and we're going to look at our last two reactions when I give you predicting products, meaning I give you the reactants and you're going to give me the rest of it. So we're at the top there, and we're going to look at single replacement reactions. Okay, for this, you really are going to need your periodic table whenever we are doing these reactions now, and it's not even the front side of the periodic table that's so important, it's the back side. Because when we did this lab last Friday and we put the metals in, and when you're looking at these reactions, so let's kind of look at all of these, and it's like, how do I know that it's a single replacement? Look at here again. Look at what they have in common. It's a single metal and a compound, single metal and a compound, single metal and a compound. Okay, remember on the lab on Friday, I think you did 12 different reactions. Did all 12 reactions happen? No, they didn't. And it's because this metal has to have more energy in order to kick out the other metal. Well, how do I know that? Is it something you have to memorize? No. No, it's not something you have to memorize. Okay, look on the back of your periodic table. You should have a chart that looks very similar to this chart right here. And so as I'm looking at that chart, it's going to be on the back side of it, and it's called the activity series. And it has lithium at the top. Yours is even nicer. Well, it has it by the name of the element all the way down. And if you notice, there to where you can see it goes down to gold. Well, look down here at the bottom. These are gold, silver, platinum, copper. Where have you heard of those metals? Hopefully you're thinking your jewelry. And these are your least active, which is a good thing. We're making jewelry out of metals that aren't very reactive. I'm going to throw them in acid, I'm going to throw them in water, they're not going to explode. That's a good thing when you're trying to make some jewelry. Look it up here. Lithium, potassium. These are my group 1s and my group 2s. They're the most active, and it's all about who wants the electrons. So you know these over here in group 1s, group 2s. These are the ones that want the electrons, so they're more stable when they're in a compound than when they are in an element, so that's why they're going to form a compound. So what you have to compare then, back over how it works. So you want to know, can magnesium kick out iron? It can kick it out if it is more active or if it's higher on the chart. So look at right here. Here's magnesium. Compare it to iron. There's your iron. So does magnesium have more iron than to kick out, more energy than to kick out iron? Yes. So that means, yes, I can make a compound. So however you want to write it. What does that mean? Well, it means iron is going to be left by itself, and I'm going to now have a compound between magnesium and nitrate. Well, nitrate is a -1, magnesium is a +2, so when you write the formula, MgMO3 2. So first you still have to make the correct formula, then go back and balance it. Because then I go, okay, well 3 nitrates over here, 2 here. So that means I'm going to have to put a times 3 and then a times 2 to give me 6 nitrates. So that means 2 irons, and with my box around my magnesium, the initial 3 magnesiums. So these are a little bit more involved, but you have to use this activities chart. And again, you don't have to memorize it. We just have to know how to use it. Okay, so now compare this one, copper to zinc. So find copper. Here's copper. So I'm comparing. Does copper have enough energy to kick out zinc? No, it doesn't. It's below it. That means it's lower energy. So what's going to happen? Nothing. You can write no reaction. Or just that NR stands for no reaction. Okay, remember all those coppers you did on Friday? A lot of you sat there and looked at your well, and that copper just sat there at the bottom. Why? Because look at how low it's on the energy chart. Copper cannot kick out very little. It can only kick out mercury, silver. Okay, we did see that. You did see copper kick out silver. It's one of the only ones that it can kick out. Okay, how about zinc kicking out copper? So you look, well, here's zinc. Can it kick out copper? Yes. Okay, now zinc, remember, it's one of those, we know it's a +2. Now looking at these, some things to remember. Copper is going to make a +2. Iron will make a +3. That zinc is always that +2. And again, if you have to use these, I will give them to you, if you know, on the worksheet that we're going to be doing tomorrow. I'll give you the charges of a transition, or give you some way that you will be able to know the charge it's going to make in that compound. So zinc a +2, sulfate is a -2, so that means its formula is ZnSO4, and then copper is what's going to be left out. Notice it doesn't matter if I write the element first or what I write first, the order doesn't matter. Okay, let's balance it. Well, if we look, everything is balanced. That one's already balanced. Okay, now this one might look a little bit different. Magnesium to kick out a hydrogen. Well, look it on your chart, and this is also in your chart. It says hydrogen, and in fact, on the periodic table, it has it in parentheses to let you know, hey, this isn't a metal, but you know what? It works just the same. So right here, here's my hydrogen. Exactly the same. You still want to know, can it compare? This hydrogen is going to be in an acid when you see it with an acid, but it comes out as H2. That's why we have the 2 in the diatomic. But it's the same thing. You have to compare. Is magnesium higher than hydrogen? Yes. This reaction will happen. Remember, magnesium is a +2, so when you write the formula for magnesium chloride, +2 -2, hydrogen comes out as the diatomic, so then you have to balance it. That means we'll have 2 of the HCl's. Okay, these 3 I'm leaving for you, and it's a good place for us to start tomorrow. I'll be checking your work on those for tomorrow. Okay, that's single replacement. Single replacements, you use the activity series. Okay, let's look then at our last type of reaction, double replacements. On this, I would also add right above it, these are also called precipitation reactions. And what's a precipitation? A precipitation, remember, is the solid. These are the reactions you were doing today. And so, do all precipitation reactions happen? No, I think you saw that. Just because you mixed 2 things together didn't mean you always saw something happen, something reaction. So how do I know if this one's going to happen? Okay, on the back of your periodic table in the very middle, you have right here, it says the solubility rules. And you're looking at the solubility rules right here in the middle. This is what you're looking for, double replacements. This is going to tell you if it's insoluble, that means it's going to make a precipitate. So see right here, if it's insoluble means it's going to make a precipitate. Insoluble means does not dissolve. If it does not dissolve, it makes a solid. So we're going to use this. Now, I will have to be honest, this is one of the worst solubility tables I've seen, but that doesn't mean it's impossible. It's just not the clear, so we're going to spend more time kind of reading it. So if we look at this, you have to look at the partnership. Over here, the majority of it are your anions. There's only one cation. This is ammonium. So this is saying any compound with an acetate is always going to be soluble. That means it's always going to be aqueous. You're never going to see a solid. No exceptions. Ammonium, all ammonium compounds, no exceptions, are all going to be soluble, no solid. Same thing, nitrates, cyanides, chlorides, all of these down here, they will all be soluble. They're going to be aqueous. Okay, then we start getting a little weird. So look at my bromide compounds. They're all going to be soluble unless, these are your exceptions. This means silver bromide will make a solid. Lead 2 bromide, PbBr2, will make a solid. Mercury 2 bromide will make a solid. So these are exceptions over here. These are the only compounds that will make a solid. Same thing with my chloride. Silver chloride, lead chloride, mercury chloride are going to be solids. Same thing for your iodides. Okay, let's look at over here. Sulfates. Most sulfates are going to be soluble unless it's strontium sulfate, barium sulfate, lead sulfate, mercury sulfate. Those are the ones that you're going to see. Okay, then look at its switches. This is where you just really have to be careful reading this. These are all then insolubles. So the only exceptions then are the ones that are going to be, these are all carbonates then are insoluble or going to make a solid unless it's an ammonium And anything, remember, alkalis is group 1. So sodium carbonate, lithium carbonate, potassium carbonate are all going to be aqueous. Same thing with my phosphates. So the table kind of switches on you. So you just have to, again, we don't have to memorize this. You just have to be able to read it very carefully. So let's go back to the chart. How do I use that? Okay, double replacement. So that means, remember, these guys are going to switch partners. We have a double switch. So I need to make a sodium nitrate compound, +1, -1. Now we do have to look at the states. And then I need to make a silver chloride compound. Then you have to go back to your chart and say, okay, will one of these make a solid? So if I go to my chart, what's it say? All nitrates, because my first one is silver nitrate. No, that doesn't make a solid. That means this is going to be aqueous. And then my other one was silver chloride. Well, most chlorides are aqueous except for silver chloride is an exception. That means that it is a solid. So no solid means it's aqueous. It's going to dissolve in water. But this means you're going to see a solid. You would see a precipitate form. It's going to get cloudy. Silver chloride's a white solid. You would see a solid form. Okay, let's look at down here then. What am I going to see? Lead and potassium are going to switch places. So lead will form with iodine. Potassium is going to form with nitrate. Double switch going on. Now I drew these arrows two different ways. It's however you see it. So some people like looking at this to realize those are going to switch partners. Some people like kind of seeing what the new partners are going to be. So it's however you need to look at it to be able to see that. So now look at this. Lead is a 2. So that means lead will be a 2. So lead, iodide, and then I have potassium nitrate. Again, I'll look at my reference chart, look at my back of my periodic table. Well, I know anything with a group 1, anything with group 1 will never, ever, ever make a solid. When I used to make you guys memorize that, that was one thing you just knew. Anything in a group 1. So I know I'll never have a solid with a group 1. Okay, lead, the bigger, the heavier the compounds, most likely you're going to get a solid. Lead iodide, if you look again on this chart, most iodides are soluble unless it's lead iodide. That means it's an exception. That means it's insoluble. If it's insoluble, that means it's going to make a solid. So you're going to see this. This is actually that yellow solid. Okay, let's look at what happens here. Same thing. We're going to switch. So iron is going to be with chloride. That's a straight line. And hydrogen with sulfur. Okay, iron makes that +3. So that would be an iron 3 chloride and H2S. Okay, now looking at this, I just kind of realized we didn't go back. You know what? I didn't balance this one. We can go back and balance it. And so to balance it, I would need to put a 2 there and a 2 there. Okay, now looking at this, these are some additional ones that you can have on the worksheet or some things. I doubt that this would show up, I have to admit, on a CA, but this is a molecular compound. This is going to actually come off as a gas. In fact, it's going to kind of smell like a rotten egg because this is going to be aqueous. So there's 3 things that drive making a precipitation. That means the reason a precipitation will happen is if we produce a solid, a liquid, or a gas. So if we start making some molecules, get that liquid or gas, or you make an insoluble compound, that's what's going to make these reactions happen. So this reaction would happen. Now if we look at this, we need to make this even. So we'd have to put a 2 here, 3 here, which means we'll have a 6 here. Looking at that. And so then I have what? Oh, you know what? I just realized this is a 2 here. Sorry, my mistake. So that means we just make this a 2. And so that means when we're balancing it, it's much easier. All that we'd have to do is put a 2 there. Sorry, my mistake. I didn't even look at what the iron charge was. Don't change the charges right now. We'll talk about what happens when they change the charges. But if it's an iron +2 here, don't do what I just tried to do. Don't try to change its charge. Go ahead and if it's a +2 here, leave it a +2 there. Sorry about that. This is why we use a pencil. Okay, last one. Look at this. This is an acid and a base. Another reason, so we've made the solids, we've made gases. Well, what happens here? So I get H is now going to go with OH, sodium with the chloride, sodium chloride. Well, I know that that dissolves because anything with a group 1. Okay, let's look at what we have here. HOH. What's another way we can write HOH? H2O. That's a liquid. That's why this reaction. So this is an acid-base reaction. Acid-base reactions happen because we make a liquid. Precipitation reactions happen when we make a solid. So this is what we're going to be practicing tomorrow in the next couple days. It's just looking at these and being able to draw the products when I give you the reactants. See you tomorrow.